So hardware is ready, but without code it's just a brick. And the software stack for RoboRover is split into three main parts. First, the firmware on ESP32, that's the nervous system checking sensors and moving motors. Second, the Python brain running on my PC, that's the frontal cortex handling high-level logic and memory. And third, the AI server running a local large language model that actually thinks and decides where to explore. Let's break down how they all talk to each other.
To make these systems communicate efficiently, especially with the AI, I switched to using TOON token-oriented object notation. It's a structured data format designed specifically for LLMs. Unlike JSON, which is full of wasted tokens like braces and commas, TOON uses significant white space and headers. It can cut token usage by up to 40%. This means the AI thinks faster and can remember more context, because we aren't filling its brain with syntactic junk. It's cleaner for humans to read, too. The firmware is written in C++ using the Arduino framework. It's the low-level warrior. It handles the fast stuff that needs microsecond precision. It manages the four-wheel servos, the LiDAR servo, and reads the IMU for balance. Crucially, it hosts the WebSocket server. The onEvent function catches the commands, and while the AI speaks Tune, the Python brain translates that into high-speed binary or simple JSON for the ESP32 to execute quickly. This split lets the AI be verbose and smart, while the robot stays fast and reactive. On the PC side, we have the Python application. This is a bridge. It connects to the ESP32 via Wi-Fi to control the body, and it connects to the AI server to get the intelligence. It manages the session, tracks the rover state, and handles the short-term memory. When the leader data comes in, the Python script parses it and converts the arrays into a compressed tune table. It sends this table to the LLM, effectively saying, here is the room geometry in a format the AI can parse reliably without hallucinatory syntax errors. This is the core logic. I'm using a local LLM, specifically Qwen 4b, running on an RTX 3070. The Python script sends the tune context, and we force the LLM to reply in tune format as well. Instead of struggling with closing JSON brackets, the model just outputs a clean list of keys and values: action, move, distance, 50. The Python brain parses this using custom tune parser I included in the repo, validates it, and then converts it to a motor command. It makes the pipeline significantly more efficient, though I'm sure there's still room for optimization. And finally, the interface. It's a single page HTML app stored on the ESP32. No React, no heavy frameworks, just vanilla HTML, CSS, and JavaScript. It connects to the same WebSocket to listen in on the conversation. That cool radar view. That's just HTML5 canvas drawing points based on the LiDAR data array. It's passive. It watches the data flow between the brain and the rover and visualizes it for us humans. It also lets me take manual control using a specialized joystick logic. And here's the cool part. You can upload new HTML, CSS, or JavaScript files directly to the ESP32's file system without reflashing the entire firmware. Just drag and drop your updated UI files, and the rover instantly serves the new interface. It makes iterating on the dashboard incredibly fast. One last thing, telemetry. The firmware constantly polls the MPU 6050 accelerometer and broadcasts the pitch roll and signal strength to all connected clients. This means I can see exactly what the rover is feeling in real time. If it hits a bump or starts to tip, the dashboard warns me immediately. It's all about that data loop: sense, think, act, and visualize.
So that's the stack: C++ for the body, Python for the brain, TOON for the language, and the local large language model for the soul. It's a bit complex, but I hope it's logical. See you.